Alright, wind power students, welcome back. We're going to continue now talking about different weather type terms and climate type terms that will be useful to us when we're discussing wind power, so we can just sort of use them and, well, we know what each other's means. But today's lecture, which is about El Nino and La Nina, takes a little bit of context to understand why we need to care about this at all. If we are going to be deciding where we're going to put some wind turbines or solar power generation or whatever, understanding where to do such things would be a whole lot easier if there wasn't a lot of year-to-year variability to the climate. If each year's winter at a given location had the same average temperature, or the same average precipitation, or the same average wind, boy, it would be a whole lot easier to figure out what we want to do about where to put those wind turbines, or where to put those solar arrays, or whatever. But in practice, that isn't the way it works at all. Any given location has a great deal of interannual variability to the climate. Interannual as in like from year to year, comparing one year to the next. There's a lot of variability to the weather and climate a region from one year to the next. You already know that wherever you're from and whatever the weather is wherever you're from, you know that some winters are snowier and some are less snowy, and some summers are drier and some summers are more wet, and so on. There's a lot of variability from year to year. That's called interannual variability. Let me just show you that that's not just in the kinds of phenomena that you experience when you experience the weather, like rainfall and temperature, but even somewhat more abstract ideas like pressure. Like, for example, here is a map of the average sea level pressure in January all around the world, and there's areas of where, on average, we expect areas of higher pressure, which are in greens and yellows and reds, and there's, on average, areas where there's lower pressure in January. But if you just pick some January, like I just picked January 2015, you can see it's not exactly the same. The pressure patterns are related, but they're not exactly the same in January 2015 as they are on the average. And we could have done this kind of analysis with any kind of meteorological variable like temperature or precipitation or wind speed or whatever, cloud cover, so if you're talking about solar power or whatever, and any other year's January. It didn't have to be January 2015. In fact, January 2015 is in some ways kind of a bad choice. That was a fairly close to normal or average year, but it would have worked for that too. And this makes you wonder, why? I mean, if I'm going to have to worry about, gosh, I'm putting some wind power turbines up on some ridge line someplace, but some years we're going to get a whole lot of power, we're going to get rich, and some years we're not going to get enough energy to pay the bills. What caused this? What are the sources of this interannual variability to our climate? Now, let's get some of the bad ideas out of our way first. It is not due to changes in the amount of energy we're getting from the sun. It isn't like a hot summer is caused by the sun being hotter than normal, and a cooled winter is caused by the sun being less hot than normal, or something like that. It is true that there is a tiny bit of variability in the output of the sun based on things like sunspots and so on, but that is way... that has like climate implications over many years, not like why one winter is different from another. It's not like the rules that govern the atmosphere change from year to year. This happens to be a way of writing the so-called Vorticity Equation, one of the most important equations in meteorology. It isn't like, oh, well, some years that works and some years that doesn't, and that's why we get fewer storms one year than the other. No, the rules of the atmosphere, the physical laws, they are what they are. We don't get to change them. We don't have any discrepancies on that. Another whole area that people get the idea of is maybe there's some kind of weather cycle. Like, weather repeats itself. Like, previously in the past there was a period where it was wet followed by a period where it's dry, and now we're just repeating that pattern. It doesn't mean that there aren't phenomena in the atmosphere that have these sort of oscillating patterns. In fact, we're going to be seeing one today, but the idea that somehow whether it's a pattern, like as in the weather is repeating itself, that's not what we're going with here. That's tinfoil hat territory. Now, there are actually multiple sources of variability between one year and the next. One important source is volcanoes. A major volcanic eruption, like Mount Pinatubo in the early 90s, can change the climate both regionally and globally. For several years after Mount Pinatubo erupted, the global climate was like a degree cooler than it had been before the eruption, just because of all of the smoke and ash and aerosols that the volcanic eruption has put into the atmosphere. Okay, that can be an important reason why a year is different from another, but those kind of super eruptions, they don't happen that often. Their effect dissipates over the course of a year or two. That's not really the most important one. The final part of this chapter is going to be about the North Atlantic Oscillation, a phenomenon in the atmosphere that causes some year-to-year variability, especially for the weather in Europe. But if we're looking for globally, what is the biggest, most important, single largest source of interannual variability? The main reason why one year looks different than another, whether you're talking Omaha or Indiana or some other corner of the world, the number one reason why one year looks different than another is a phenomenon called El Nino and La Nina. There's not a single easy dictionary definition of this phenomenon. Let me kind of give you some verbiage here and we'll kind of pick it apart. I wrote that it's a pattern in which ocean temperatures in the eastern tropical Pacific, like off the coast of South America, are either unusually warm or unusually cold for a period of about a year. The water temperatures off the coast of South America and out into the central equatorial Pacific are either going to be quite warm, several degrees above normal, or several degrees below normal. And the changes in this sea surface temperature distribution are associated with changes in weather patterns worldwide. Now, let's start picking this thing apart. I said warm or cold. Well, actually, that's why there's two terms here. In tropical meteorology and tropical climatology, we tend to use those words El Nino and La Nina as being associated with the warm and cold phase of this phenomenon. So it is an El Nino event when the water temperatures in the central and eastern Pacific are unusually warm, and it is a La Nina event when the water temperatures in the central and eastern Pacific are unusually cold. These terms El Nino and La Nina have a very long, complicated, not entirely clear history as to why we call these phenomena the way they do. El Nino, of course, is Spanish for the boy, La Nina is Spanish for the girl, and feel free to take my tropical meteorology class. You have the prerequisites for it, and learn. We'll spend weeks on El Nino and La Nina, but right now we're just getting kind of a little overview of the phenomenon here. So, but just to be clear, when we talk about El Nino and La Nina in this context, we're talking that those Spanish terms refer to what's going on in the ocean aspect of this phenomenon that we're talking about. That's in contrast to how the atmosphere changes in this phenomenon. We're going to see that there are changes in the winds, there's changes in the pressure, there's changes in the jet stream, and that phenomenon that's going on in the atmosphere is called the Southern Oscillation. This just has to do with the fact that oceanographers and atmospheric scientists are different communities, and they discovered this independently. The oceanographers tended to call it El Nino and La Nina. The atmospheric scientists found it in different data sets like pressure and temperature and rainfall, and they called the Southern Oscillation. But the two phenomena are completely related. Ocean changes and the atmospheric changes are, the atmosphere is changing the ocean is changing the atmosphere. It's purely mankind that makes us think there's a difference here. Okay? It's the Earth, atmosphere, ocean system working to create this phenomenon. And that's why a better name for the whole thing, a more modern term for this whole phenomenon, is El Nino and the Southern Oscillation, which we write the acronym ENSO, E-N-S-O. And you'll often hear these use the term ENSO rather than El Nino and the Southern Oscillation. In fact, you might have noticed that the name of this presentation is ENSO, or the PowerPoint presentation the name was ENSO, and so on. That's a better recognition of the fact that this is a coupled phenomenon. The ocean isn't changing the atmosphere isn't changing the ocean, they're working together. I can imagine that nothing I've said so far has helped some basic questions that are on your mind, like, what does this ENSO thing look like? Or why does this ENSO thing happen? Or why would changes in the water temperature in the Pacific Ocean cause changes in weather patterns worldwide? And those are all fantastic questions, and I'm going to try to kind of brush over some gentle ideas about this. But again, for a much bigger understanding of how this works and what's the mechanics of what's going on, not just at the surface of the ocean, but down deep in the ocean, and how that affects weather patterns worldwide, you need to take tropical meteorology. it's a fun class, and I enjoy teaching it. Now, so let's kind of get a sense of what this looks like. Now, what I did here over here on the left is I put a plot that just shows what the mean sea surface temperature distribution looks like for January. That is what water temperatures all across the Pacific Ocean just happen to look like. There's good reasons for all of the salient features of there. I mean, you might notice there's some cold water off the coast of South America, and you might notice that there's sort of that cold temperatures in the Eastern Pacific, and so I wish we had time to talk about all that right now, but there isn't a lot of wind power reason to talk about that. So here's our sea surface temperature, or SST, to use the term that climatologists and atmospheric scientists tend to use, sea surface temperature. Here's our sea surface temperature distribution on average, and if I pulled a particular year out, I'm going to take a look at January 2016 and do the same analysis here, I can see that they are not exactly the same. But it is actually kind of hard. I mean, I can definitely see there's some warming going, I don't know, there are all kinds of stuff going on here. It tends to work better to take the difference between the observations at the present time, like we're talking January 2016, versus the average. The difference makes it more obvious to see where there's patterns that are warmer and colder. And when you take the difference between those two plots, you get what I show you here, where there is a very large area of warm sea surface temperatures across the equatorial, central, and eastern Pacific at that time. This is what we would say is a positive sea surface temperature anomaly. The waters are warmer than average. Hopefully this word anomaly isn't a big problem. So, like, we would say then that January 2016 is part of an El Nino event. And in fact, it's part of a very large recent El Nino event where the water temperatures were very warm. You can see we're talking about, at that particular time, about 3 degrees Celsius warmer than normal, which is a lot. Think about the amount of heat it takes to increase the temperature of the water over an area, roughly the size of the continental United States, and you start realizing this is an enormous amount of energy being moved around in the climate system. In contrast, I could pick a different year. This happens to be January 2011, and I computed the sea surface temperature anomalies, the difference between the water temperatures in January 2011 and the mean water temperatures in January. And you get that in 2011, you see this huge area of those purples and blues that shows that this is an area of cold water across the central and eastern Pacific Ocean. We have a negative sea surface temperature anomaly. The water temperatures are colder than usual, and that means that January 2011 was apparently part of a La Nina event, meaning that we had cold water across the central and eastern Pacific. Now, this is a pattern. This happens over and over again. It doesn't mean like as in it's a pattern, like, I don't know, you punched in and punched out of your clock. No, but it's something that happens. And once it happens, there are consequences and so on, and the atmosphere in the ocean will play out in similar ways each time this El Nino or La Nina event happens. And just to give you a sense of what it looks like when they happen here, I've got a plot here that illustrates tropical meteorologists divide the oceans up into little pieces, these little regions, these little rectangles. And the diagram I have up there happens to illustrate a few of them that are in the Central Pacific, called like Nino 3, Nino 4, Nino 3.4. And just because I happen to have it handy on a bookmark, I just chose Nino 3.4, a region of the Central Pacific there. And if we kind of pull out the sea surface temperatures at that region, we have a whole bunch of buoys and stuff out there to monitor this stuff. What you see is that there have been periods of time over the last, about 15, 16 years or so I have on this diagram here, where you can see that the water temperature was above normal, or more like El Nino in that region of the world. And you can see that there were periods of time when the water temperatures were unusually cold, and I'm pointing out areas on that diagram there where you see that there are La Nina events happening. And we've been monitoring this for better than 50 years out there. Here I added another 50 years of Nino 3.4 data up there along the top of the diagram just to prove to you that we've got it. Okay, between merchant ships and buoys and things like that out there, we've been monitoring this for 50, 60 years now. If you actually take a look on that colorful diagram there and look at those El Nino events that have happened in the last 16, 17 years or so, you can see that a typical El Nino event lasts about a year. You'll often hear like a meteorologist or a climatologist talk about, 1982 was an El Nino year, okay? Because most of them do last about a year, although the range is about 9 months to maybe 2 years or something like that. But that's about how long it takes for this area of warm water to form and move and eventually dissipate, or in the case of La Nina, for the cold water area to form and move around and dissipate and so on. And so the actual event lasts about 1 year on average. And again, if you kind of take a look both at the colorful diagram and look at each El Nino event, or you go look at the longer one I have up there at the top of the diagram, you can see that the events occur typically on average about 4 years apart. One El Nino and then the next one. The next El Nino will happen on average about 4 years later. There is a bit of a range. Sometimes it's as short as about 2 years later, and sometimes it's as much as about 7 years later, but there's kind of an interannual scale to this thing. It lasts, it's about 4 years apart. From the period of ENSO is about 4 years from one El Nino event to the next. And typically, again, if you take a look at the diagram here, most of the time between one El Nino event and the next one, there'll be a La Nina event between them. Not always, but most of the time. That does tend to be the pattern, is there tends to be an El Nino for a year or so, and then we move into a La Nina for a year or so, and then we move back into an El Nino for a year or so. It's just part of the natural climate variability of the Pacific Ocean. I also want to draw your attention to the fact that there is a very wide range in how strong these El Nino events are. You can see how some of these events that I'm pointing to had much warmer water temperatures than the other. In fact, that 2015-2016 El Nino event was very large in terms of the water temperature anomalies across the Nino 3.4 region. Why? Why is this happening? Okay, again, I would be so excited if you decided to use this as motivation to take tropical meteorology, to learn all about how this is driven by Kelvin waves in the deep ocean and blah blah blah. It's all really cool stuff, but we just kind of need a very superficial description of this so that we can start thinking about consequences of this for wind energy and so on. So what I did here is I just took the mean or normal conditions, the average sea surface temperature distribution across the Pacific, and let's start putting some stuff on this diagram here. Now, all across the equatorial Pacific, as is the case with more or less all of the tropics, we have trade winds. Trade winds, remember, are those easterly winds that are very persistent down near the surface of the Earth, and they're easterly, so they're blowing from the east to the west. In fact, if you were like the happy little wind power engineer setting up wind power farms on little tropical islands along the equator there the way I drew it, you'd be a happy wind power engineer under normal conditions that are neither El Nino nor La Nina, because I wish I could make animated make that windmill animated there, but the trade winds are lovely for generating wind power. They're very persistent, they're fairly strong, they last for a very long time. So those winds are blowing across along the equator, all the way from like South America towards Indonesia and Australia and so on. Now, why the trade winds are there, that's a bit of a complicated issue associated with general circulation, which again, we're not going to get bogged down. Remember all those like Hadley cell, all that kind of good stuff. But a big part of the story is, in general, there is higher pressure in the eastern and central Pacific, and there's generally lower pressure off to like Australia, Indonesia, Southeast Asia, and so on. And because we're in the tropics where there's not a lot of Coriolis force or, geostrophic balance stuff going on, the flow does kind of just go from the higher pressure in the east towards the lower pressure in the west. That's the only force acting on there. These trade winds there, as they blow across the surface of the ocean, are actually exerting a stress on the ocean. If you pushed your hand along, slide it along a stack of magazines on the table, imagine if you do that. Well, your hand is exerting a stress on the stack of magazines, and they start slipping along with you. Okay, that's stress. And it's kind of like friction or something like that. The atmosphere is exerting a stress on the ocean over a very large area. I mean, this is more than 10,000 kilometers long and hundreds, if not thousands of kilometers wide, where this trade winds are doing. This is exerting an enormous stress on the surface of the ocean, pushing water from like South America towards Australia. And the water kind of piles up over by Australia and Indonesia under this condition. Picture a swimming pool, a big swimming pool. Now, the water is flat, right? It's the same height above the center of the earth all the way across the swimming pool. Now, if you put a really big fan at one end of the swimming pool, you could kind of picture that if you blew that fan across that ocean, that pool, and you just kept pushing, if you could get in there and measure really super accurately, can you picture that the far side of the pool, the water would kind of start piling up? Like there would be kind of a little bit of a pile of water in the far side of the pool where the wind has been pushing the water. In the same sort of way, that happens across the central Pacific Ocean too. All that trade winds putting stress on the surface of the ocean makes the ocean physically higher in the western Pacific than it is in the eastern Pacific. It's not an enormous amount, it's like 50 centimeters. Which is astonishing that we can measure such a thing, by the way. That, like, you know, the surface of the ocean is literally like 50 centimeters higher in the western Pacific than it is in the eastern, but we can do that with satellites and so on. And think of the energy involved. If you had to hold up a half a meter of water the size of, like, you know, the western Pacific Ocean, there's an enormous amount of potential energy here. Now again, oh my gosh, in tropical meteorology we have a great deal of fun talking about how all this works and so on. But that is a whole lot of energy holding back this pile of water in the western Pacific. We've got this area of low pressure off there in the western Pacific too. I want you to think of that as something like a heat low when we were talking about monsoons. I mean, it's kind of like it. The water is warm there in the western Pacific and is creating an area of low pressure. And in the same way, out there in like the eastern and central Pacific where the temperatures are colder, think of that as making that high pressure system there. It's kind of like the opposite of a heat low. It's actually closer to that than you might think, but that is a good way to think about it. Okay? The low pressure on the western Pacific is being created by that warm water out there. And that high pressure in the central and eastern Pacific, which I have drawn a little bit farther south just to keep it out of the way of the other symbols I have there on the map. Think of that as being kind of like the opposite of a heat low. The colder water out there is creating higher pressure. And we have this lovely normal condition, and under these normal conditions, we get an enormous amount of rain in like Indonesia and northern Australia. There's all this warm water piling up in the western Pacific, and warm water is great for forming precipitation because you have a lot of evaporation off that warm water. So that creates a lot of water vapor in the atmosphere available to be turned into precipitation. And by conduction, heat from the warm ocean warms up air at the surface, and those air parcels at the surface start to rise, and rising air causes thunderstorms and so on. The western Pacific is a very rainy place under these normal conditions. So I've kind of built this diagram here that shows you persistent trade winds and happy wind power engineers all along the equator, low pressure in the western Pacific, higher pressure in the eastern Pacific, and rainy conditions out there in like Indonesia and Australia. And that would be our normal or average condition across the Pacific Ocean, but it doesn't stay that way. Sooner or later, something goes wrong to screw this up. Either that pile of water out there in the western Pacific that just keeps getting higher and higher, 30 centimeters, then 40 centimeters, then 50 centimeters, then 60 centimeters, gets built up over the course of months and years as the trade winds push more and more water up against the western Pacific. Sooner or later, that pile is big enough that the trade winds just can't hold it back anymore. That's one possibility of things that can go wrong, and that warm water along the western Pacific is going to start sloshing away, regardless of what the trade winds want. Or something comes along and makes the trade winds weaker, some kind of like synoptic scale disturbances, or something comes along and makes these area of high pressure, low pressure that are kind of what's supporting the trade winds weaker. But either way, something sooner or later is going to go wrong, and we throw our Pacific Ocean into an El Nino pattern, where everything is different. That warm water that was out over like the western Pacific, over by Indonesia and Australia, comes sloshing back. Just like in the metaphor we had about the pool. If you were using a fan to blow the water across the pool, and you actually had managed somehow to pile the water up over there on the far side of the pool, what's going to happen if you ever turn off sooner or later that pile is either so big the fan can't hold it back, or if your fan ever gets turned off, someone trips over the cord and the fan gets turned off, the water's going to come sloshing back. And that's exactly what's happening in the form of oceanic Kelvin waves. Take tropical meteorology. For the water to start coming back, that warm water comes sloshing along the equator towards the central and eastern Pacific. creating this warm conditions across the places that normally have very cold water. During that time, the trade winds get very weak. Maybe the weak winds are what caused that water to start coming this way, or maybe changes in the pressure pattern are what makes the trade winds weak. But either way, the trade winds get really weak during an El Nino event. Look at those unhappy wind power engineers. Their boss is telling them, why aren't we getting enough electricity? Well, we can't do anything about it. There's little to no wind. In fact, what wind does happen during El Nino is often from the west, against the trade winds. Look at how that warm water in the central and eastern Pacific is associated with unusual thunderstorms out there in the central and eastern Pacific, a place that normally has very little thunderstorms because the water underneath is so cold. Now we have all these unusual thunderstorms. See how the pressure pattern at the surface has changed. Now we have higher pressure because the water's kind of colder out there off Australia and Indonesia. And we have lower pressure out there in the eastern and central Pacific. Again, I put the L a little bit farther south so that it wasn't quite so cluttered right there. But that lower pressure, again, think of it as kind of like a heat low. Well, we've just put all this warm water out there, the surface is warm, and we're making like a heat low out there. It's not exactly like that, but pretty close. You get all that precipitation, you get all that evaporation out there in the western Pacific. It's very wet in the eastern and the central Pacific during the El Nino conditions. Oh my goodness, what a strange phenomenon. On the other hand, during a La Nina event, a La Nina event is kind of like the normal conditions, but even more so. The trade winds are even stronger than normal. Look at those big, strong trade winds there. Look at those shocked wind power engineers I have on there, okay? They're getting so much power they don't know what to do with it at these tropical islands that I drew in there. They are getting, all those trade winds are pushing cold water from over by South America. We get all this cold water conditions along the equatorial, central, and eastern Pacific. We've got that pile of warm water out there in the western Pacific is even bigger and warmer than usual, and actually in this case a little bit off the edge of the map. Because the trade winds are pushing in that warm water so far off to the west. We've got the pressure pattern there with low pressure over near Australia as even lower than normal, and that higher pressure over there in like the central Pacific is even higher than normal. And we get all this, we get even more rain than usual in Indonesia and Southeast Asia and Australia and so on. La Nina is sort of like the normal condition plus, okay, even more going on. Now, it can be hard to picture how these things happen and play out. I actually, oh gosh, a long time ago, like in 2005 or something like that, put together a very cheesy animated video about this that's called El Nino and Star Wars or something like that, I don't remember. But anyway, the link is on this slide right here, and I'll also make it available to you on Blue Line. I would suggest that even though it's cheesy and old and all that kind of stuff, it has really good animations that show how this looks like as the water temperature anomalies move around and so on. So I would recommend, after this video or something like that, go and watch that because it will really help you understand what that pattern looks like. Now, you'd be perfectly justified saying, wait, Dr. Shruggy, did the trade winds cause the changes in the ocean? Like, we strengthened the trade winds and we pushed the water around? Or was it the other way around? Did the ocean cause the changes in the pressure and the trade winds and so on? This seems really hard to think about, and you're right, because that's just how human brains work. The ocean and the atmosphere are working together here. Okay? They are part of a coupled natural system that it's only because we tend to think of oceanography as a different thing than climate and so on, that we think that one should be causing the other. We think in this very linear way. But that's not how the real atmosphere, ocean, planet system works. That's why ENSO is such a good name, because it makes it very clear we mean these things are working together, the ocean aspects and the atmosphere aspects. Now, it would be really handy if we had a nifty way to measure this, to actually be able to quantify, yes, right now this is El Nino conditions, and it has been for the last few months, or from this year to this year was La Nina conditions. We do have a way of measuring that. It's called the Southern Oscillation Index, or the SOI. And it is a measurement that has been around for a really long time. The early research in El Nino and the Southern Oscillation by atmospheric scientists was all about, they could measure that there was something strange going on with regard to like pressure and winds across the Pacific. Now, like if I just bring back this diagram here that showed what the average conditions across the Pacific look like, it'll help us see how this Southern Oscillation Index is going to work as a measure of whether it's an El Nino or a La Nina going on. I mean, that area of low pressure over there near Australia and Indonesia, and that area of high pressure out there in the eastern and central Pacific, they're kind of key to the atmospheric aspects of ENSO, right? I mean, they were a big part of the reason why the trade winds were blowing the way they were and so on. They're a big part of the story. They're going to be changing based on the water temperatures underneath them and so on. Well, as it happens, we got a little lucky on this one. There are two weather stations more or less right near the center of that area of low pressure and right near the center of that area of high pressure that have been running for a really long time. Darwin, Australia, which is kind of the very northernmost tippy top of Australia, and Tahiti, which is a little tropical island more or less right under that H that I have there, are both places where there have been well-calibrated, well-designed, well-maintained weather stations for like 150 years, which is very unusual. Very unusual to have weather stations that have run that long. And so we can, well, wait a minute, if they're at the center of where these pressures are changing, we can define a number, the Southern Oscillation Index, or the SOI, as being the difference between the pressure at those two stations. It's defined to be pressure at Tahiti minus pressure at Darwin. Now I put it as squiggly equals because it's actually more like it's a function of that, okay? It's actually a little bit more complicated than how we compute the Southern Oscillation Index. But that will give you a good sense of how it worked, and this would be an okay, you could define the Southern Oscillation Index this way. So it's the pressure at Tahiti minus the pressure at Darwin. So, for example, during an El Nino year, where pressure is quite low near Tahiti out there in the Central Pacific, and pressure is quite high over there in Indonesia and Australia, Tahiti minus Darwin will be a small number minus a big number. The Southern Oscillation Index will be negative. So we'll know we're in an El Nino event if the Southern Oscillation Index is negative. Or we could go the other way around. During a La Nina event, when we've got these big strong trade winds and these big surprised wind power engineers across the Pacific there, well, Tahiti minus Darwin. During a La Nina event, the pressures are usually high at Tahiti in the Central Pacific, and pressure is even lower than usual over there in Australia and Indonesia and so on. So a big number minus a small number, you're going to get a positive number. So the Southern Oscillation Index will be positive during a La Nina event. And in fact, we have this all the way back. I just happened to pull up the Australian Bureau of Meteorology's website, happened to have a lovely little interactive activity about the Southern Oscillation Index. You can see, you can look at it for all of, gosh, that goes all the way back to the 1870s on this particular diagram. And you can see it bounces up and down. There's times when the Southern Oscillation Index is positive, and times when it's negative, and times when it's near zero. We can actually zoom in a little bit here and look at just like the last 5 or 6, 10 years apparently, and you can see how like we've had this recent El Nino event in like 2015, 2016, when the Southern Oscillation Index was negative, and we have other times along the way where it was negative, and lots of other times where it was near zero, and so on. And in fact, we can look back across like just the last, I don't know, what is this, about 30 years or something like that, and we could see 3 really famous El Nino events. The most recent event over there farthest to the right is the very strong El Nino event that recently ended across the tropical Pacific. You might be remembering that there was a big El Nino event in 97-98. I don't know how young you would have been in 97-98, but many students would remember that. That was a very large El Nino event. You can see how the Southern Oscillation Index was very negative for a period of a year or so. And the biggest El Nino event that we've ever observed was in 1982-1983, where is the biggest sea surface temperature anomalies and the biggest, the most negative values of the Southern Oscillation Index during that time. Okay, wow, I get it. This is some cool thing that goes on, is sloshing motion as the warm water moves around in the tropical Pacific. Wait, Dr. Shraggy. Why is that affecting the weather all around the world? I mean, that was why, odds are you're not going to get a job doing wind power along the equator at some tropical island, in the Central Pacific. Then I could definitely see why this would matter. But actually, it makes differences to the weather all around the world. And what causes it to have impacts all around the world, believe it or not, is those strange thunderstorms. Well, they're not strange, they're just unusually where they are. across the central and eastern Pacific during the El Nino event. You might remember we had this diagram at that time, where because the water is unusually warm, we get these unusual it's unusual to have thunderstorms in that part of the world. This is going to cause changes to the way the jet stream is flowing in both the northern hemisphere and in the southern hemisphere. Now, this is a little bit of a complicated subject. It's called Rossby wave source, and you have to know the mechanics of Rossby wave. Oh my goodness. No, take tropical meteorology. I'd love to teach you all that. But I can kind of show you an analogy. Picture you're at a beautiful mountain stream, and there's a rock in the stream. The water flows over the rock, but as it flows over the rock, it isn't like, and then the water just goes back to being flat again. Once the water has been perturbed by the rock, you get those standing waves downstream from the rock, right? Even several meters downstream potentially from the rock, there's still kind of waves in the stream that are caused by that rock that was in the flow. There was an obstacle to the flow that created this train of waves downstream from where the rock was. Well, that's just a metaphor, but it's actually surprisingly close to what actually happens due to El Nino. The surprising thunderstorms out there in the central and eastern Pacific create features in the upper atmosphere that act kind of like a big obstacle to the jet streams. And you end up getting a pattern of troughs and ridges downstream from the big thunderstorm complexes and so on that are in the central and eastern Pacific. There is a pattern of like a big trough in the central Pacific and a big ridge in the western United States and western Canada and a big trough in the eastern United States and a big ridge over the Atlantic and so on, and this pattern continues. In the northern hemisphere, this is the pattern that sets up in the jet stream downstream from where the unusual thunderstorms happened in the central Pacific. Just like downstream from that rock in the flow, you still get waves in the flow. This particular pattern that you're seeing here has a name. It's called the Pacific North America pattern, or the PNA pattern. It is the main pattern that happens in the northern hemisphere during El Nino. There's a similar sort of thing that goes on in the southern hemisphere, etc., which I can't think of its name right now. Anyway, this is important. We have set up a strange set of troughs and ridges in the jet stream. And this changes everything, because changing where the jet streams are and where troughs and ridges are changes where cyclogenesis is going to be happening. So we're going to have different areas where like storms are going to be created and changing their track, changing the track of the path that the cyclones and so on are following. It's going to change where air masses form. It's going to change how air masses move, which is going to be changing like where fronts are coming through. Remember, fronts are kind of the leading edge of those air masses are moving. There's going to be a huge impact in terms of like how this affects, these changes in the jet stream are going to be changing where hurricanes can and can't form and what kind of tracks they can and cannot follow, all of which is year-to-year variability. This is interannual variability of the weather around the world. And it's all being set in motion by these changes going on in the Pacific Ocean. It's pretty cool stuff. Alright, again, man, we spend weeks on this stuff in tropical meteorology. For a much more thorough explanation, by all means, talk to me. I'd love to have you in that class next time it's taught. In the meantime, let's answer a couple questions about El Nino and La Nina. Question 1. During an El Nino event, the sea surface temperatures, or SSTs, in the central and eastern Pacific are unusually blank, and the Southern Oscillation Index is blank. Are the sea surface temperatures cold or warm, and is the Southern Oscillation Index positive or negative during an El Nino event? Alright, look through your options, choose from one of those four, and get some feedback before you move on to question 2.